Okay, so first of all, I'll just say I'm like really excited to be here and to get to talk to you all. I remember being like an elementary school student and coming to one of these talks, and yeah, it was really a special moment for me. So it feels kind of full circle to be back here and get to talk about some of the stuff we're working on. Now, it's only my name on this slide. My advisor is David Kipping. I've had the luck of working with a lot of amazing mentors and other colleagues. A lot of them are sitting here, so more people than I can thank. But it's like in astronomy always, it's not just me. It's a lot of other people, which is one of my favorite things about the field is it's a really big team effort. I'm going to be talking today about from wobbles to worlds, how we can develop a framework to detect the unseen. And as some of you astute viewers might have already noticed, I've started with a picture of the total solar eclipse from this past week. I was really excited when I realized I was talking several days after it, because the core of my research is really just looking for these same eclipses, but around stars that aren't our sun. So here's a nice image of the total solar from this week. Here's one from 2017, a composite of a series of 7 photos of the partial eclipse and the total solar eclipse. And so I'll start with just a simple question of why do solar eclipses happen? Why do we see these total solar eclipses on Earth? It's really just a geometric happenstance. So these aren't to scale, but their relative sizes are good enough to get the derived effect. So we take the Earth, the Moon, and the Sun, and we trace out what their angular diameter is in the sky. You find that they have approximately the same angular diameter. And what that means is when the moon passes in front of the sun, even though it's much smaller physically, the relative distance of the two objects means that the moon can block out essentially the entire sun. And this is a consequence of the fact that the distances between the Earth to the moon, which is about 380,000 miles, and the Earth to the sun, which is about 150 million kilometers, has the same ratio approximately to the diameter of the two objects. So they're both approximately ratios of 400. And so when you have that effect, that means they have the same angular diameter. It's about 0.5 degrees in the sky. That's why they block each other. You can also see this if you ever looked at a full moon, and you shouldn't look at the sun, but if you have a sense of what the relative size of the sun is, they're about the same. So they have the same approximate angular diameter. In our solar system, it turns out this is the only moon and planet system that we know that has this geometric occurrence. So for example, we could look at the Mars-Phobos system. And if we look at that system, the moon has a smaller angular diameter from Mars. And what's really cool is thanks to instruments like Perseverance. This is a real image of Perseverance rover. So the big rover is Perseverance, and the little guy in the background is the Ingenuity helicopter, which recently went offline. But this is actual footage from Mars. And in a couple years back, the Perseverance rover was able to capture an eclipse of Phobos passing in front of the sun. And you'll see here that even though it's passing right through the middle, or approximately the middle, it only blocks out a small portion of the light. So if you've ever seen a partial eclipse, it's not that the moon passes fully in front of the sun, it's that it passes on an angle. Whereas here, the relative angular sizes aren't the same, so you get only a partial blockage. Okay, so this is eclipses. I'm going to be talking today about transits. So typically when we talk about eclipses, we're talking about moons passing in front of the host star from a planet. When we're talking about transits, we're talking about a planet passing in front of its host star as viewed from another planet. And so here is approximately what you'd expect for a Venus transit in front of the sun. And in fact, we can observe that as well. So this is an image from one of NASA's solar telescopes. And this is a real transit of Venus, which are the black dots passing in front of the sun, is viewed from a telescope that's orbiting the Earth in a low Earth orbit. Okay, so that's transits. Now it's an exoplanet transit. Now we're going at a completely different scale. So now instead of objects in our own solar system, we're talking about stars, other stars in our Milky Way galaxy. And so I've done up this stretching, and you can see that we're blocking much, much less light. In fact, what we find, and so now I've flipped the angle. Now we're looking at planet passing in front of its star face on. And we'll see these 3 stages of the orbit. And if we observe the brightness of the star over time during the orbit, that when the planet passes in front of its host star, it blocks a portion of the amount of light. And so these are called exoplanet transits. And I'll just go back again to click through that. The idea being, so you're looking at the light received from the star. In this first section, the planet isn't blocking any of the light, so the relative brightness is constant. In this portion, the planet passes in front of the star, and so you block a certain percentage of the light. And then again, for this portion of the orbit, we're not blocking any of the light, so it's flat again. And so these are these transits, exoplanet transits, that you might have heard about, that has, as Justin has said, have been very successful at finding exoplanets. Yeah, so the transit method has been used to find many known planets. To date in total, astronomers have discovered, confirmed about 5,600 planets. I think it's 5,602. I can't see my slide. And of that, I think about 4,000 of them are using transit, like 4,200 have been found with transit. So the vast majority of the planets we know about have been discovered via the transit method. We can see that also on this diagram, which shows the number of planet detections by method year to year. And you'll see that there are two real workhorses in this exoplanet transit game. One is the Kepler Space Telescope, which launched in 2009, and one is TESS. So Kepler launched in 2009, operated for 9 years, went offline in 2018, and then TESS launched in 2018. So Kepler observed over 500,000 stars. It discovered, to date, 2,779 planets with an additional about 2,000 candidates, but it only observed about 0.25% of the sky. So what Kepler did is it observed a very specific field for 5 years. That one location of the night sky, with a 1 meter telescope, was able to observe relatively deeply and find both bright stars and faint stars, kind of everything in that field. TESS took a very different approach. So TESS is basically just 4 CCDs essentially in space. There's no big telescope lens. But because you're in space, you don't have the atmospheric contamination, so you can still observe the brightest and most nearby stars. And so TESS has observed around 200,000 stars. It's confirmed around 432 stars, but there's an additional 7,000 or so exoplanet candidates. But it's observed about 93% of our night sky. And how it does it is with these tiled sectors. So you're looking at schematic of how TESS observes the night sky. Each of these rectangular sectors is observed for 27 days. And so what it does is it tiles the southern hemisphere for about 1 year, and then it flips and it tiles the northern hemisphere. So it launched in 2018. It's now on had a primary mission of 2 years. It got extended. It's now on its second extended mission, and hopefully will be operational for years to come. And here's a comparison of TESS versus the Kepler field. So that main field in the top in yellow, that's what Kepler observed for the first 5 years. 5 years in, 2 of the reaction wheels on the telescopes failed, and so we weren't able to hold stable on that one location in the night sky. And so what the engineering team was able to do, which is pretty spectacular, is figure out that they could stabilize it enough to point for short periods of time at the ecliptic. So that's why it observed this area in the middle. And this diagram is only good for the first 2 years of TESS. That's why it doesn't look like it covered 93% of the night sky. It's now kind of filled in some of that, more of that space. Okay, so one of the major results of the Kepler Space Telescope, which you might have heard been advertised and discussed, is that there are more planets than stars in the Milky Way. And so with those stats that I gave you, this might be surprising, because Kepler observed 2,700 planets after observing 500,000 stars, and I'll just tell you there's about 100 billion stars in our Milky Way. So how can we claim that there are more planets and stars when we only have seen 2,000 out of an observed 500,000 in 100 billion stars in our Milky Way? And so we have to understand not only the strengths of the transit method, but also the drawbacks of it. And so I'll say there's 3 main ones. The first is there's a low probability of planets being properly aligned to transit. So for an Earth-like planet around a Sun-like star, the probability of transiting is 0.5%. What this means is if we're looking at a Sun-like star and we know there's a Earth around it in our neighborhood, just geometrically, if you look, it only transits if it passes in front of it like this. If the orbit is at all inclined, it won't transit relative to our viewing angle. And the geometry, the spacing between these successive or between the objects means that for most of these orbits, you wouldn't actually pass in front of the star. And in general, the further the planet is, the less likely it is to transit. And so what that means is that even though we've only discovered 2,000, there's likely many more planets orbiting these stars, and we can use statistics to extrapolate out what are the other planets around the system based on the numbers that we detect. Additionally, it's just harder to detect smaller planets. So the bigger the planet is, the more light it blocks from the star. And so a fundamental property of transit observing telescopes is like the minimum detectable transit depth, which equates to the minimum detectable planet size. And the last thing is that there are multiple true astrophysical signals that can mimic transit signals. And so a lot of effort's been put into kind of statistical differentiation between what's a true positive and a false positive transit in these data sets. Okay, so I suggested that in many cases, planet could be orbiting a star, but it's geometrically not transiting, so by the transit method, we could never find it. And I said that in many cases, planet or a moon could be too small where our telescope isn't sensitive enough to detect it. So how might we hope to find these objects in these stars? And so what we can do is look for these wobbles. And so I'll run this through a couple times. But the idea here is if we see a planet transiting, this green planet in this case, and there's a moon orbiting that planet, its orbit won't be a perfect circle. Instead, the moon and the planet will orbit each other as they orbit the sun. And so if we look at what our transit looks like, you'll find that successive transits will be early or late based on the effect of this interacting moon. So in our diagram here, in purple would be what would be the expected transit of this planet with this moon around it. And you could see that I've put like tau 0 is the transit time if there's no moon around the planet, and tau TTV is this observed transit. Additionally, though, you can get a similar effect if you have two planets orbiting the star, and the interaction between the planets create a similar effect. So you don't get this really quick effect that we then observe a longer alias of that effect, but you observe that the planets' interactions themselves induce this same TTV, or this same wobbling effect that we can observe in the transit time. So again, here, the green planet is a transiting planet. The idea is that this blue planet is interacting with that green planet, and we can try to distinguish it by that motion, by that wobble. However, in practice, we don't see the image on the left. All we see is these transit times on the right. And I purposefully made it such that induced transit variation is the same for the moon and the planet, because oftentimes that's what we observe. All we can see is these variations. This is like what our data set might look like of a series of 5 transits over time, is you see that the planet is sometimes early, it's sometimes late. So these wobbles in the orbit of the planets induced by other physical objects in the system induce these transit timing variations we call TTVs. And I'll just say that it makes it difficult without knowing what's causing the wobble if you don't see both objects in the system to differentiate between them. Okay, so that's kind of the whole ramp-up preface. Now I'll get into what my work is on. And so my project is how can you try to go from these wobbles, so these TTVs that I've spoken about, to these worlds, so either to detecting moons or planets. And I'm going to do it via 2 routes, either the exomoon corridor or the exoplanet edge. So hopefully after today you have a little sense of what are these paths from wobbles to worlds and how we're trying to break these degeneracies between these signals. So I'm going to show you some real data now. Brace yourself. There's a lot of time and effort that went into these. If you don't understand the whole figures, that's fine. Ask me questions afterwards. I've spent 3 years looking at these, so yeah, be warned. Okay, so what you're looking at here is 2,600 systems from the Kepler Space Telescope. They're all transiting planets. Each black dot is a transiting planet. What I've plotted here, though, is about 1,900 of them that favor TTV signal over no TTV signal. So essentially what we did is we fit periodic signal to the observed transit times, and then we fit a model with no variations, and then we ask the question, which is statistically favored? And in about 75% of the time, it favors these TTVs. So it seems like these variations are very abundant in our data set. And if we're just thinking about the solar system that we know the best, the stellar system we know the best, there are 8 planets. Most planets have moons. There's a lot of objects interacting, so it's probably not surprising that these transit times aren't perfectly consistent. I'll also note that, as I said before, on the x-axis here is the orbital period, which means what is a year for this planet. So the Earth would live at 365 days on the x-axis. And then the y-axis is the amplitude of the TTV signal in minutes. And I'll just put here where the amplitude of what Ganymede, which is the largest moon of Jupiter, and our moon would live. And then I'll also add here Kepler 1625bi, which is a exoplanet candidate that was identified by a previous grad student at Columbia, Alex Tichy, and David Kipping. And that's what the amplitude would be for that system if it turns out to be real. So I promised 2 effects. Let's get into the first one, the exomoon corridor. So the idea behind the exomoon corridor is that we observe planetary transits once every transit. By definition, you only get 1 data point every year for that planet. But the period of the wobbles of a moon-planet system, the true period, will be equal to the period of the moon, right? Because the moon is orbiting this planet, it's invoking a periodic signal. So that's the true period. But we sample it on a period which is equal to the period of the transiting planet, which by definition is always going to be longer than the period of the moon. So we'll always observe an alias of this true TTV period. And when I say alias, it sounds like a big scary math word. It's something we see every day. If you're driving down the highway and you look out your window and you see a car tire moving really quickly, the rotation rate of the wheel is faster than the frame rate of our eyes. And so we can't see the true motion, the true period of the tire's motion. We observe an alias of it. We observe a longer period. That's what's happening there. So it's the same effect, but with moon data. So simulated here is how that happens. So in gray is what a true TTV signal would look like for a moon orbiting a planet. In black is where we would observe the TTV observations. And you can see if you fit a sinusoidal model to that data set, you get the red curve. And this red curve is an alias period, which is longer than the true period of the signal. And I'll just skip a lot of math and derivation. I'm happy to talk about it as much as you want after this. But in 2020, David Kipping showed that a consequence of these aliases is that 50% of moon-induced TTVs would live between 2 to 4 times the period of the host planet. So it induces these fast TTV periods that's equal to 2 to 4 times the period of the transiting planet. What's interesting about that is if we plot that on the diagram, this is what this shows. In white is these simulated aliased exomoons, and in yellow are known planet-planet TTV systems. You'll see that not only do moons oftentimes induce TTVs in this short period range, but planets don't very often induce periods in this exomoon corridor. So there's only a contamination rate of about 1%. About 1% of the known planet-planet TTVs fall into this fast period range. So this is a good place to look for possible new moons. And so that's exactly what we did. This is, again, this same data set that I showed you before. But now I'm showing just a downsampling that we did. And so we applied a series of 6 cuts to the data, selecting for more moon-like signals, doing things like removing systems that we knew to have multiple planets in the system, removing systems that had amplitudes that were too large to be caused by a TTV of the moon, so on and so forth. When we do that, we end up with 11 targets, but really one system stood out. And it's called Kepler 1513b. We're not really good at naming planets in astronomy. It's just like a convention, but it is what it is. So Kepler 1513b is a gas giant. So it's like a Jupiter or Saturn-like planet at 160 days. So it orbits its star once every 160 days. And now that we identified the system, we wanted to answer the question, is this unseen companion to this planet a moon or another planet? And so here's the real data of the transits. And the bottom purple is the Kepler data set. You can see the strength of this 1-meter telescope in space. There is actually a black model fit through that data, but it looks perfect. And then about 10 years later, we observed 2 more transits. So in green and blue, we observed the same transit. And then in orange and red, we observed a transit 2 orbits later. And what I've done here is we just stack them on top of each other, folding by the period. And so you could see where they all line up. And what I've plotted here is the TTVs. So what you're doing is those wobbles that I showed you before, you find the variation in the midpoint, and that's what I'm plotting on the y-axis. So you can see that in the Kepler data set alone, this is just the Kepler data, that we have this short period signal. That's a period about 2.6 times the period of the transiting planet. However, when we added in these two additional observations, we find that the short period signal persists, but there's an additional long-term period. And so this long-term period is not conducive to having a moon, and is also is what you expect from a planet-planet system. And so with this, we knew that that's no moon. And we identified Kepler 1513c, which is most likely a Saturn mass planet with a close to a 5-to-1 resonance, which means its orbit is about 5 times longer than Kepler 1513b. I'll just say that there's more systems that are still exciting in this exomoon corridor. There's one in particular, KOI 3762. And there's an additional transit in June that we're hoping to get from the ground and try to reproduce these results and see if we can learn if there's another planet, if there's a moon, what's causing these TTVs in the system. Okay, quick pause. Exomoon corridor, we're good. We know how to get from Wobbles to Worlds via the exomoon corridor. Now we're going to get into the exoplanet edge. Okay, so the exoplanet edge is the fact, and I'm going to tell you the answer now, and then I'm going to try to walk you through it, but I'm going to be a little hand-wavy in the derivation, that a planet will never induce a TTV with a period faster than half its own orbital period. I'll say it again. You have two planets in a system. They're orbiting the same star. The outer planet will never induce a TTV with a period that's faster than half its own orbital period. Why is this? So we have to remember that we observe, again, transits only once per transit of the transiting planet. I'm saying transit a lot. In this case, we're talking about the green planet as the transiting planet, and the blue planet will be this exterior perturber. What I'll do is I'll walk you through what these TTVs will look like, and I'll freeze it every time this green planet transits. And so what you see is that even though there's a faster period, faster true period, again, we're getting the same aliasing effect that we saw for moon-induced TTVs when you have a distant perturbing planet. And when I get here, I'll be able to say, so for this case, for the first half of the external planet's motion, you find that when the green planet is transiting, the other planet is ahead of it during its transit, and so it's pulling it through. When it's pulling it through, it causes an early transit, and when it's lagging on the second half, it's pulling it back, and so it's causing a late transit. And so we find that this alias, by definition, will be equal to the period of this exterior planet. Now, there's another effect that has half this orbital period. I'm not going to bother you with the math. Again, if you want to talk about it, I'm more than happy to. But I'll just say that there exists another effect that creates the same aliasing effect with one half the period. And so this induces this exoplanet edge, the minimum observable period equal to half the period of this external perturber. Okay, so we can reproduce a similar thing that we did in the exomoon corridor. We go back to our Kepler data, and we found that 22 planets, so now we're looking at 2-planet systems, and we're trying to see if any 2-planet systems induce a TTV that looks faster than is explainable, that's faster than this exoplanet edge. And we find 22 of them that do. So what could cause these? Perhaps there's another planet in the system. We know 2 of the planets are transiting, but you could pack a third planet in between the 2 planets, make it a little bit inclined so it doesn't transit, so we don't detect it, and maybe that could cause it. Maybe it's a moon. Maybe it's a highly eccentric planet. So those are the 3 options, but either way, it means that there's something more in this data set. There's more to discover, and we think it's a really exciting other path forward. Okay, first takeaway is transit method has been very successful. It's found 4,000 or so planets, which is a lot. But in the context of thinking that there are more planets and stars in our Milky Way, you could also say it's not a lot. It's not anywhere near 100 billion. So if we want to really get the most out of our data sets, we have to develop tools to try to study and search for these hidden planets. I say that, and then I'm trying to do that. So we're developing some of these tools. We're hopeful that we'll be able to build computationally efficient ways to look through these full transit data sets. And our current best bets are these searches of the exomoon quarter and the exoplanet edge, which hopefully start to craft out sections of this orbital landscape, and then we can look further and try to analyze these systems on a population level. So I'll put my roadmap back up, and I'll take any questions.